Hi viewers, welcome back to the course. In this particular video, we will be looking at a problem that was asked in GATE 2014. I remember it correctly because I remember answering this particular question myself in the examination hall. So, as I used to tell you, pause the video here, read the question, and have an answer for yourself, and once it is done, just cross check or your answer with mine. Okay, so they are asking critical damping, and there are four options. Four of them at the first look equally good for the right answer, but you need to read through the lines. They are asking what is critical damping. So before we pick one answer, let's have a look at things what we learned as part of a single degree of freedom. This thing is coming from free vibration, in which we were talking about single degree of freedom systems with damping. Okay, then according to the amount of damping present in the system, this kind of mechanical systems can be categorized into underdamped systems, critically damped systems, and overdamped systems. And what I have shown over here is the response, or in other words, it is the plot of the displacement x, which is defined like this with respect to time. To give you a bit more physical intuition of what is happening here, let's say I'm pulling this particular mass by a certain amount as given by this particular height, which is the initial displacement over here. I'm pulling it to a certain distance, and then I'm just leaving it. Then I'm just observing the response, which is nothing but the x of t function with respect to time, or I'm interested in how that x of t evolves with respect to time for different values of c. So I'm just changing the amount of damping present in the system, nothing else. Then this particular curve which you can see here, this corresponds to the underdamped system, as I have shown here. Zeta less than 1, zeta is the damping ratio. To put it mathematically, zeta is c by cc, where c is the coefficient of viscous damping and cc is the critical value of viscous damping for a particular system. It is given by 2 root km cc. So these are all additional information. These are not required for directly answering that particular question, but that's okay. Now from this figure you can see, when I'm increasing the amount of damping present in the system, or in other words, when I'm increasing the zeta value, I can see that when zeta is less than 1, motion is harmonic. It is decaying, but it is harmonic. I told it is decaying because, as you can see here, the amplitude of the particular waveform is decaying. To be more precise, it is decaying logarithmically. Okay, so when you increase the amount of damping, the motion changes from periodic to aperiodic. Now let's go through the four options. The first option reads, it is the largest amount of damping for which no oscillation occurs in free vibration. Pay attention to each of those details. It is the largest amount of damping for which no oscillation occurs in free vibration. And in the second option, it is the smallest amount of damping for which no oscillation occurs in free vibration. Again, let's assume a case zeta equal to 2. The motion is aperiodic. Zeta equal to 4 also, motion is aperiodic. And zeta equal to 1, also it is aperiodic. Which implies that the first sentence is wrong, because critical damping is not the largest amount of damping for which no oscillation occurs in free vibration. For zeta equal to 2, no oscillation occurs, and zeta equal to 4 also no oscillation occurs. So that option you can rule out. The second one, it is the smallest amount of damping for which no oscillation occurs in free vibration. Again, let's think of a case where zeta is 0.5. Then we have a periodic motion. Then we have zeta equal to 1, that I have already written there, the motion is aperiodic. So we can say it is the smallest amount of damping for which no oscillation occurs in free vibration. That makes sense, because when zeta falls below the value of 1, or let's say zeta is 0.99, then what happens? We have some amount of damping. So the C value corresponding to zeta equal to 1, or where C value is equal to Cc, that case corresponds to the smallest amount of damping for which no oscillation occurs in free vibration. Make sense? So B is the right answer. This question, for most of you, it may seem relatively simple, but I request all of you, when you are given this kind of problems, be patient and give some ample time to read through the options and appreciate or understand what each of them are conveying to you. Thanks for watching.